Good. Do you know the chapter number? I think it's chapter 21. Okay. So in this semester we are going to study electromagnetic interactions, right? Interactions. And my message here starting is that electromagnetic interactions are everywhere. So we only have 4 fundamental forces, right? There is gravity, strong nuclear force, weak nuclear force, and electromagnetism. These are the 4 fundamental interactions that we have. And gravity accounts for planets revolving around and you being pulled towards the Earth. But otherwise, it doesn't explain anything else. Like why you fall in love because of electromagnetism. Why do you need water? Because of electromagnetism. Why can you hold the paper in your hand? Electromagnetism. Everything else is electromagnetism. And why I'm ignoring these ones as well, because these ones are too deep in the layer of nucleus and they are short-ranged. So they don't go out of nucleus. Their effect is not present out of nucleus. So that's why if you are not living inside a star, they are irrelevant too. So electromagnetic interactions are everywhere. Okay? So let's start by talking about electric charge. So let me tell you, Physics 102 is nothing but high school physics, right? Except you have integrals, right? So when we come to integrals, we will say goodbye to high school. And please don't get detached from the course, okay, once we go there and you start having that barrier suddenly. Because, okay, let's talk about electric charge. You all know it, right, already. So the word electric comes from electron, but it's not. In Greek, it's apparently means amber. And amber gets electrified. It has static electricity, right? Static electricity is something that is largely overlooked. It's not very, very well understood why you get static electricity. You can still see some science nature papers involving static electricity or triboelectricity, meaning that electricity coming from friction. It's a very complicated subject, but in our simplistic view, it's basically you put fur and let's say plastic together. You rub plastic with fur and fur becomes positive, plastic becomes negative, right? Another famous example is silk and glass. Right? Silk becomes negative, glass becomes positive. You are already aware of this, right? I keep forgetting which one gets negative, which one gets positive. It's not important. One of them, there's a charge transfer there. So this idea of plus and minus comes from Benjamin Franklin. Okay, he introduced this idea that there should be 2 kinds of charges, and let's call them plus and minus. Okay. So what happens with them? Plus and minus attract, plus and plus repel, minus and minus repel also. Right? You already know this very well. So let's briefly talk about structure of matter. Matter is made up of atoms, right? And atoms have nuclei. This is nucleus. Please. Yes, thank you. So the size of this nucleus is really, really small. Okay, and what keeps nucleus together is this strong force, right? The size of the whole atom is much larger, 10 to the minus 10. Okay. So it's 100,000 times larger. It's like the whole building is the whole atom, and this dot is the nucleus, right? So what do we have inside nucleus? Inside nucleus we have neutrons and protons, right? What do we have inside protons? We have fundamental particles. So we have quarks. I should use different colors, but never mind. So plus 2 over 3e plus 2 over 3e minus 1 over 3e. These quarks are fundamental particles. By fundamental particles, I mean that in principle they have no radius to them. They are point particles. Okay? They don't. I was going to say that they don't occupy the space, but I should be careful about my definitions here. But in any case, they are fundamental particles, and protons are formed by two quarks, 2 up, 1 down quark. And neutrons are formed by 1 up and 2 down. This is just what you call genel kültür. Okay? These are neutrons. One very important part of this general culture is that protons and neutrons are not fundamental particles because they are made up of fundamental particles, right? And protons are stable by themselves, while neutrons are not stable. I think they live only for 20 minutes. Then they turn into a proton. Like you shoot a neutron, it's out in the wild. It can't go on forever. Okay? Protons are stable. How about electrons? Right? These are the electrons. They have negative E charge. Of course, you can do the mathematics and see that this has plus E charge, and this is neutral. And electrons have negative E charge. Right? So far, do you have any questions? What about electrons? Are they fundamental particles?
As far as we know, yes.
as far as we know, yes, they are fundamental particles. So this is the picture of the structure of matter, more or less. And you all know that once you bring atoms together, there are different kinds of bondings that can happen. And mainly the electrons are involved in those bondings. Okay, good. So what is the mass of an electron? Mass of an electron is 9.1 times 10 to the minus 31 kilograms. And mass of a proton is nearly equal to mass of a neutron, and they are about 1800 times of mass of electron. So they are much heavier than the electron. Do you have any questions? Yes?
You mentioned the transformation of neutrons into protons, but what about the electric charge there? Isn't that supposed to be proton?
Okay, then I'm wrong. I think there is also another particle that comes out. Maybe it's a beta decay. Are you buying this? Yes? I'm not sure. We can look it up. Or you can look it up. Please let me know. Yes, of course. We waited for you, but you didn't came. Oh. Thank you for doing that. You can watch the lecture anyways. But please sign the attendance as well. As you very importantly mentioned, what was your name, sir? Efe. As Efe mentioned, very important thing, electric charge is conserved, right? So anything that we mention, any process that we mention, we should conserve charge. Did you look it up, Efe? How neutron decays?
Proton plus electron
Plus neutrino. Very good. So, electric charge is conserved. Let me give you a brief detour towards very fundamental physics. There is this very famous scientist, Emmy Noether. Okay? She has a principle. It's called Noether's principle. And it tells you that every conserved quantity has its corresponding symmetry. And every symmetry has its corresponding conserved quantity. Let me give you some of the things that you already know. You know that momentum is conserved, right? If you do deep physics and do all of its mathematics and you know the Noether's theorem, you can show that momentum is conserved because of symmetry in space. Okay? What do I mean by that? Let me give you an example. You throw a ball, it has Vx and Vy, right? And let's say there is gravity. Goes on like this, right? And while it flies, momentum in the vertical direction changes, right? Because this gravity, G, is breaking the symmetry in the vertical direction. But in the horizontal direction, it doesn't matter whether you throw from here, or from here, doesn't matter. So momentum in the horizontal direction is conserved, right? There's a very fundamental principle deep down in physics that just find the deepest physicist that you can find and ask him to tell you one word that would explain all physics, he or she would choose the word symmetry. Okay? So, symmetry in time conserves energy. Energy conservation is coming from symmetry in time. Angular momentum is conserved whenever you have rotational symmetry. And finally, electric charge is also conserved for a symmetry that is very hard to explain even to myself. So charge is conserved because of something called gauge invariance. Very advanced concept, but you can just name drop it in a cocktail, you know. Oh, gauge invariance, it's conserved because of that, without knowing what it is. That's exactly what I'm doing right now. Anyways, so it's conserved for a very good reason, very deep reason, just like space, time, and rotational symmetry. It's another symmetry that conserves charge. What does it mean? As you mentioned, proton cannot just decay into neutron because you don't conserve charge there. As we learned, there is also electron plus neutrino. And neutrino is also there to conserve something, probably momentum or energy. Yeah. Good, very good. Do you have any questions? Yes.
There is another Veritasium video about this, about how there is no time symmetry, charge symmetry, and scientists are combining them together, so there is at least some symmetry.
Mm-hmm.
So can we really say that time is symmetric? Because the proof they were giving was that I think a fundamental particle was changing its state periodically, and one of those changes in state takes longer than the other. So if you try to go back in time, you know which way is forward and which way is backward. So there is no symmetry in time.
We have to talk in private about this,
Mm-hmm.
but I'm open to any kinds of new physics. But otherwise, come in, please. Please sign the attendance. In general, all our physical laws are time reversible, right? I don't know about this situation, so we have to talk. Okay. Now let's talk about conductors. We are still in high school, okay? If you are bored because you have seen this million times. Conductors, insulators, and other things. So materials can have metallic bonds, right? In the metallic bond, you basically have nuclei somehow aligned like this, and metallic bond is like a wave, like a sea of electrons just keeping these things together. And there are free electrons in metals. So this is, let's say, a metal or a conductor. A conductor would have, of course, the electrons that are involved in bonding, but they will also have free electrons. Okay? So free electrons would move anywhere they want. Especially if you have electric field, they would keep moving until they make sure that the electric field becomes zero. We will come back to this once we define electric field. But otherwise, you know what a conductor is. It conducts electricity. You can put electron from here, get electron from there, right? But insulators are different. In the insulators, you don't have you again might have a lattice, but electrons are more or less tightly bound. They are involved in bonding, and let me call this no free electrons. They don't have free electrons to move around. Okay? For example, this is an insulator. This is an insulator, this is a metal. Thank you very much. There is another one of this. Where is it? Yes, okay, keep it there. So, in metals, the charge would move around, right? So, for example, if you bring a positive charge here, let's say this is, let's them all be metal, metal, metal. You would actually have an accumulation of negative charge over here and positive charge over here. Of course, this positive charge is just electron deficiency, and this negative charge is electron accumulation, right? But if you bring close, let's say, a positive charge towards an insulator, then you don't have free electrons to move around, but you still would, let me show it like this, you still would pull these electrons towards yourself, so you would create some sort of a polarization. They would be like tiny bits of minus plus, minus plus, minus plus, minus plus. That's what would happen in the insulator. So electrons would not actually go to the other edge to meet the positive charge, but they would just turn that way. Okay? Does it make sense? Once we start learning about electric field, we will come back to the fundamental difference of insulators and conductors. Okay? One fundamental thing that I should mention twice at least is that for metals, charges gather on the surface. But for insulators, charges can gather everywhere, in principle. If you charge an insulator, you can charge it uniformly throughout its inner volume as well. But not for a metal, because there would be free electrons and they would just go out as far as away from each other as possible. Does it make sense? Are you incredibly bored? No? How you are not bored? It's physics. You must be bored. All right. I'm not bored. I'm just joking. Let's say I comb my hair. So let's say I have a comb here. Very bad at drawing. And if I comb my hair, it will be negatively charged. It can still attract some paper, right? So let's say this is paper. It would attract them. How is this possible? We know that paper is insulating. Well, it's possible because of this effect. Okay? So it would create a little bit of negativity just right next to a little bit of positivity. A little bit of negativity just right next to a little bit of positivity. Okay, I used negative with blue, so let me just make this one also red. Okay? So that's how, okay, let me just change this drawing. Negative, a little bit of positive, a little bit of negative, a little bit of positive, a little bit of negative. Okay? This all you know from high school. Now comes the part that will actually come up in the exam, which is Coulomb's law. Although this will definitely be in the exam, doesn't mean that these are not relevant. Okay? You are still going to use those concepts very fundamentally in your problem solving. So, Coulomb's law is due to Charles Augustin de Coulomb. He has studies in many different areas. Electricity is just one of them. And Coulomb would tell you that if you have a charge Q1 and Q2 separated by a distance d, or let's call it r, separated by a distance r, then you have a force. The magnitude of the force is going to be K times Q1 times Q2 over r squared. You already knew this, right? So do you remember the value for K? Yes? You just answer. Yes.
1 over 4 pi epsilon 0.
Very good. And which is equal to approximately 9 times 10 to the 9, right? Newton meter squared over Coulomb squared. Very good. Now, why we bother ourselves with this K equals 1 over 4 pi epsilon 0? Because epsilon 0 is a very fundamental thing. It's called permittivity of free space. Okay? And the value for epsilon 0 is 8.854 times 10 to the minus 12 Coulomb squared Newton meter squared. Okay? This is the magnitude, and the direction you already know, right? Concerning the direction of the force, whenever you have positively charged charges, you just draw a line connecting them, okay? And the force will be along that line, and it would be repelling. This is how you find the direction of the force, and this force is the same. So force on the first one due to the second one, this is the magnitude of the force, second one due to the first one, and the magnitudes are equal, but the directions are opposite, right? So you can write down 1, 2 is equal to minus F 2, 1. This minus is because of the direction. Do you understand what I mean when I write 1, 2? Force on the first one due to the second one, force on the second one due to the first one. There is no F11 or F22, so the charge would not repel or attract itself, right? Any questions, comments, ideas? Let's do an example. So here's an example. I have 2 microcoulombs here. It's actually negatively charged, and let's say plus 3 microcoulombs here. Bless you. And I have 1 centimeter distance. Okay? What is the direction and magnitude of this force? Okay? And let's say this is the plus I direction. So, let's say this is the object 1 and this is the object 2. So what is F12? let's find the magnitude first. So the magnitude of F12 is K times Q1 times Q2 over R squared. I forgot to put magnitude here, absolute value here, yes. So that's how you find the magnitude. When you are finding the magnitude, you don't care about plus or minus. You start caring about plus or minus once you find the direction. All right. Can you please help me out? So what do I have here? 9 times 10 to the 9 times, what do I have next? 2 times 10 to the minus 6. Are you following? Yes? Is it super easy? Then that's why you are silent? Okay. Thank you very much. And then the other one is 3 times 10 to the minus 6 divided by, what do I have as R? 10 to the minus 2, because it's everything should be in meters, right? 10 to the minus 2 squared. So I basically have 9 times 2 times 3, and then I have 10 to the 9 minus 6 plus 4. Do you agree with this? Can you please check, because I keep doing mistakes. Is it 54 times 10 to the what? Plus 1, minus 1? Plus 1. So 540 newtons, right? So you can see that even microcoulombs result in a huge repelling force. It's like 54 kilos nearly. What about the direction? So F12 force on the first one due to the second one, since it's negative and this one is positive, right? So F12 is pointing in this direction, 540 newtons, and the other one is in the opposite direction, 540 newtons. So F12 is 540 I, and F21 is negative 540 I. Are you happy with this? Unitler yok. Puan kıracak mısın hocam? Okay.
It could have been a trick question.
Hmm?
It could have been a trick question.
Yes.
Saying that, are you happy with this? And if you said yes, then
Very good point. I usually don't care unless it's clear that you don't know it. You know, sometimes it's clear that you know it and you just don't write units because it's pedantic. Do you see what I mean? I wouldn't force pedantism on you when I know that in the paper that you know it. But what really happens is that we have all these 42 hours of lesson, right? And in the final, you only remember KQ over D squared, like from somewhere in high school, okay? Unless I see that you have improved, you have let high school go, you know how to go in this level, no problem. Those kinds of mistakes shouldn't be a problem, okay? So don't get stressed about this pedantic stuff. But then again, so be on the safe side and write the units, the vectors and whatnot. Do you have any questions? Yes.
If those electric forces are too strong, then how can an atom stay together?
Oh, very good question. You mean a proton? Yeah, I mean, like you have a neutron and they are packed with protons, right? No. You are asking about proton and electron.
Yeah.
Yes? Okay. Very good question. The answer is in quantum mechanics, unfortunately.
Both of them.
Okay. The first one is how on earth I can pack plus charges together, and the answer to that is the strong nuclear force. Strong nuclear force keeps them together. Okay? But strong nuclear force is acting within this range. Okay? Outside that range, it doesn't affect. Or if it would crush the whole universe together, right? We are lucky that it's short-ranged.
So this is why we have radioactive.
Radioactivity is more about. Radioactivity is complicated. It's a combination of strong and weak nuclear force. So you can explain beta decay with weak nuclear force. You can explain some other things with strong nuclear force. But in general, those interactions bring a richness inside the nucleus. So it has its own mind, its own world, and it can make transitions, and that's how you get radioactivity. Coming to your second question, which is how come the electron wouldn't just spiral down and hit it, right? Well, classically, the answer is that rotational motion is already accelerated. So you have a force towards here, but you also have an acceleration towards there, which is v squared over r, right? And that's how planets also stay in orbit, right? But again, classical theory, this time classical electromagnetic theory, tells you that whenever you have an accelerating body, it would lose energy. So classical theory actually tells you that it would spiral down and hit the nucleus. Okay? But quantum mechanics resolves this issue. And I can't, unfortunately, teach you quantum mechanics. I would love to, but yes.
Does it matter where we put the minus sign between the force? Like, can we put it?
Yes, it's fine. It's fine if you, yeah, don't worry about this kind of stuff. Okay?
Okay.
If you want. Where do you want to put it?
Like F12 will be minus 540 newtons, and the other one will be equal.
No, because actually I have defined which way is plus. Okay?
I didn't see that.
Yes, so the direction matters here. This is plus I direction. This is minus I direction. Very good question. Okay? Thank you.
So these two particles are aware of each other. How they are not that they are
Aware. Very deep question. Can you repeat your question? It was too exciting and I couldn't listen the rest. Yes.
like minus particle is how they are know that there is a closer plus particle and if they are pulled that.
Okay. I think we will get a better answer once we deal with electric field. So this is what also bothered Newton and Einstein, spooky action at a distance, right? So you are there, I'm here. We are used to things moving when they touch or interact when they touch, but we are not touching. Still, I can affect you. How is that possible? This was resolved by it's not really resolved, it's just a model that explains it. That whenever you put your negative charge here, you actually create an electric field in the whole universe, pointing inwards towards this charge, right? Okay? And when you put the other charge over here, it's just affected by that electric field. Okay? Are you happy with this explanation? No? By the way, this charge, when you put it, will also create its own electric field, which is also in this direction. And that's how it will actually attract this one. But if you want to go deeper, you can ask the following question. If I jiggle this, how long will it take for this to realize that it was jiggled? Do you understand my question? Yes? It's not instant. It's not at an instant. So it's not like you jiggle this one is immediately jiggled. No. It's transferred, this information of jiggling is transferred with the speed of light. Yes. And the whole thing is governed by photons, by the way. The whole electric field, magnetic field, all the electromagnetic interactions are actually giving back and forth photons. So photons are carriers of electromagnetic interaction. Okay? Let's talk about superposition principle. Very important principle. Superposition principle. So, superposition principle tells you that, let's say you have 3 objects, okay? And there might be, let's say this is plus, let's say all of them are plus. So there will be a force on this one because of this red one. Let me call this red. And this one is magenta. There will be also a force in this direction because of the third one, right? So if you want to find F1, the total effect on F1, total force, you can just simply sum up F1 because of the second particle plus F1 because of the third particle. That's allowed to do. This may be, of course I'm allowed to do. What else can happen? But this only happens because electromagnetism is a linear system. If it was non-linear, it wouldn't happen. Okay? You don't get twice healthy when you get twice the medicine, right? It's non-linear. The real world is non-linear, but the world of electricity and magnetism is quite fair and linear. Ne kadar ekmek o kadar köfte. Okay? Linear. So you can sum them up. Let's do an example. So, example. This is the first particle and it's minus 1 microcoulomb. Let's call it the first particle. Where should I put 1, 2, 3? Let me make them smaller and call it 1, 2, 3. This distance is 4 centimeters. This distance is 3 centimeters. This is 90 degrees. This one is 5 centimeters. Very good. All right. Plus 2 microcoulomb here. Plus 3 microcoulomb here. So which one should we find? Let's find F1. Okay, and let me define this direction to be plus I and this direction to be plus J. So to find F1, I have to sum up F12 and F13. Let's start with F12. What is the magnitude of F12? 9 times 10 to the 9 times. What should I have? Q1, 1 microcoulomb, 1 times 10 to the minus 6. I'm not using the I'm using just the absolute values because I'm going to find the absolute value for now. What is the second charge? Please be more interactive.
İlkokul çocuğu gibi olmuyor.
Nasıl?
İlkokul çocuğu gibi olmuyor. 2, 1.
Kaç olsun? 1.2 falan mı?
Demek istediğim şey tekrar edince.
It's fine. Just like take it at this level and you can do the rest yourself. But I'm sure none of you will do it, but unfortunately in the final I see that even this one somehow didn't diffuse there. And I hate being judgmental. I'm never judgmental. And that's a very bad thing that I find about myself. I never judge people. But this is what's going to happen. Like, you somehow get detached, and you could do it in high school, but you can't do it in midterm because you think that we are not going to ask this kind of stuff. But we will. We will ask very simple questions like this. So you should be able to do this. Good? Are we good over there? So stay motivated until the end. You can do this. You have it. What's your name? Ali Kemal. You are not happy. Don't worry, we will have integrals.
I'm not stressed at all.
Yes, you are bored.
No, I'm not bored as well.
What was the question then? What was the thing? I misunderstood it then.
You're asking us to say the numbers.
Of course, because then it's a monologue.
I
Right.
know, but I find it childish to say 1, 2.
Yes? Is that why you are... This is very important to me. So is that why you are not speaking? Because it's childish? No? Because you don't know? Not that one either. So why you don't speak?
You're not used to it.
So it's because you are not used to it, because it reminds you of high school?
No, in high school, you're also not doing it.
Okay.
Like, it feels like noise. Like, if all of us say the same thing, then I feel like I'm interrupting you, so...
But I'm asking you.
So, okay, it's okay, then I think it's not childish at all.
So can you please say it, if you can? Okay. Like, there is always 1, 2, 3 people who would take that on their shoulders, okay? And it's totally fine. You are doing a service to community. Okay. I was because otherwise you are going to get detached from the course. If I ask and you don't answer, ask and you don't answer, then my monotonic voice will put you to sleep. All right. What is the distance? 3, yay. 3 times 10 to the minus 2 squared, right? Okay, 9 times 1 times 2 divided by 9. Just find my mistakes, even that is very important. Did I make a mistake here? No. Thank you very much. See, it's merrier together. 10 newtons from the first one. Please. Yes, there you go. Very good. 20 newtons in which direction though? Is it up or down? Down because they are attracting, right? Each other. So, what's your name? Melis. You tell me whether it's plus J or minus J.
Minus 2.
Very, very good, Melis. Excellent. Excellent. So, we have done F12. Notice that over here I have the magnitude, over here I have the whole vector with its negative sign and with its direction. Then let's go a bit quicker and do F13. The magnitude is not very hard to do. The direction will be trickier. So, what should I write here? 1 times 10 to the minus 6, and the next one is 3 times 10 to the minus 6. See, it's a lot of fun. 5 times 10 to the minus 2 squared. Are you following? 9 times 3 over 25. Now you can't. Now you can. 10 to the 9 minus 6 plus 4. So what is 27 over 25?
1.08.
How can you do that? Wow. So you get 10.8 newtons. Right? Are you happy? Now comes the direction part. And it's a bit tricky. You have to use trigonometry. So, is it pulling down? It is pulling down here, right? And we know the magnitude. It's 10.8. But we need to deconstruct it into its x and y direction, right? So there should be 10.8 times, what is that vector? Can I say 10.8 times 4 over 5 here and 10.8 times 3 over 4 here, 3 over 5 there? Would you agree with that? Yes? Everybody's clear on that? Anyone who didn't understand can tell me, please? No one. Okay. So, that vector is F13 and it is composed of 10.8 times 4 over 5 in the I direction, because it's plus I in this direction, right? This is plus I. What is your name? You are confused, right? Yes, tell me.
Could you explain again the directions?
Yes, of course. Do you see this vector pointing this direction? That's plus I. Okay, so I put this number and I put plus I. This is not minus, this is plus. Did you already tell me your name?
Yes, thank you so much.
Bengisu. Bengisu, what about this one? Compare it with these vectors.
Minus J.
Exactly, very good. So you are going to have minus 10.8 times 3 over 5j. Okay? Very good. We are almost done. We are now going to use this formula over here. So let's duplicate it. Put it here. So F1 as a vector is a vector sum of F12 and F13. And we can just write F12 is minus 20 Newton J. You see, I forgot to put newtons here. So I can just do Newton here. I don't care about that. I will know when you know. And I will not take any points from you. All right. What is 10.8 times 4 over 5? 10 point. How can you do that in your head? Are you kidding me?
I just multiply both the numerator and denominator by 2, so then I can divide it by 10.
Brilliant. Can you do this one as well?
And it is 6, 5, 6, 6.6.
Excellent. It's negative 6.48 J. All right. Everybody's happy? So what do we do next? Let me just put the whole thing as newtons. What do we do next?
Add the ones with the right vector sign.
Yes, we add all the i's together, and there's only one I, so it's 8.64 newtons of I. And we also add all the j's together, negative 20 and negative 6.48. So we have negative 26.48 newtons of J. And that's our F1 force. Okay? So, thank you very much. Take good care.